today we're going to continue our study of integration, and specifically we'll be going over integration that involves the inverse trigonometric ratios. This is inverse sine, inverse cos, inverse tan. Those of you that aren't familiar with the term inverse, it's the arc versions or the versions that you get after you press shift. So these are often used when we're rearranging trigonometric ratios. And so it looks a bit like this. So we're not so much integrating the inverses directly because we don't really have a method for doing that. So what we're going to be doing instead is we're looking at integrals that give us the inverse ratios. So if we integrate, now mind you, this the dx on top just means that this is the same as the integral of 1 over square root 1 minus x squared dx. So I hope that makes sense, but it's essentially the same thing. It's just when we multiply by 1, when we multiply 1 by dx, we just get dx on top, but some students are a little bit unfamiliar with this setup. But yeah, so this basically just means this is 1 over root 1 minus x squared, and that's going to give you inverse sine of x plus c. And because it's the same as sine, except now it's negative, and the difference for tan is that it's positive and there is no square root. So if you see any of these fractions, then you should use these expressions to give you your inverse sine, your inverse cos, and your inverse tan. And now, again, just like all the integral relationships you do in this, you don't really need to know where they come from as much as you need to know how to use them and when to use them. So it's important to get familiar with these formulas and to know what they look like, at least well enough so that you can identify which ones you should be using in a given situation. That way, when you come across a question that has something like this in it, you know, oh yes, when I integrate that, that becomes inverse sine. And so then you can just do that. And again, the plus c terms are all just arbitrary constants of integration, which you should have seen plenty of times before. Anyway, moving on to an example, we see this. So now we want to evaluate from 0 to 1, and this is essentially 1 over the square root of 1 minus x squared. Now, it's got a square root, so we know that it's either going to be sine or cos. And there's no negative in the front of it, so we know that it has to be sine. So what we're going to do now is we're going to take our integral from 0 to 1 dx over the square root of 1 minus x squared. And so now we know from those previous formulas that the integral, I also forgot, no, I didn't forget the dx actually. From here, we know that from the previous formulas that when we integrate this, we're going to get our inverse sine terms. We're going to get sine minus 1 of x, because that's our given variable. And importantly, because this is a definite integral, we're not going to add our constant of integration, because instead I'm going to define the boundary regions. And now from here, it's just a normal integration question. And we're just using regular substitution for a definite integral, which is we take the high boundary, which in this case is 1, and we subtract the low boundary, which in this case is 0. So let's do that. So this becomes sine inverse of 1 minus sine inverse of 0. So where do we use sine inverses? We normally use them when we're finding the angle of a given an angle that we want from a given side. So when we have sines of some angle equaling to 1, what sort of angles are we using? Well, we're going to be using things like 90 degrees and then multiples thereof. So inverse sine of 1 is just going to give us 90 in degrees, or because we're now no longer really using degrees in this course, we're going to use pi on 2 for radians. And so now when we're using for 0, if we have sine of some angle equals to 0, what's the most basic example of that? Well, sine of 0 is 0. So we're going to so pi on 2 minus 0. So this is going to then give us an answer of pi on 2. And that's our integral. So this integral is equal to pi on 2. And if you get stuck on any of the inverse sines or inverse coses or inverse tans, you can always just put them into your calculator and it'll give you the answers that you want. just be careful in case it does ask for an exact form. That when you're doing this, you're converting between radians or degrees, because your calculator will likely give you your answer in degrees, and even if you set it to radians, it's not going to give you your answer in terms of pi. It's going to give it as an inexact form, so you have to make sure that you've got the exact form, which is pi on 2. So it might be worth going back and practicing with some of your inverse trigs. However, moving on, just like most of the stuff we do with sine, cos, and tan, there's the most basic version, and then there's a little bit of a harder version which involves varying some constants. So before we had where all of these a's are in these formulas, we had a 1, and then we just did sine minus 1, sine inverse of x, not x over anything, because really we were doing it x over 1. So what's happening here now is we're making a more general case where we can have any arbitrary number a squared in that left term. But other than that, all the ratios stay the same. You know, sine and cos both have their square roots, and cos has a negative sign, and tan has a positive sign and no square root. So it's really important to just make sure that you know that these are just the same formulas with just a little bit of extra generality added from this a squared, which we then propagate using it as a on the bottom here. So now let's look at an example of where we can use this. And so that's this. So now we've got a 3 squared. Sorry, gave it away a bit there. We have a 9, so we know that our a must be 3 squared, which means a is equal to 3. So here we know that our a is 3, so that'll be useful later. But we've also got a square root, so again, we know it's either sine or cos, and again, we've got a positive sign at the front, so we know that it has to be sine, not cos, because cos has a negative. So now let's start with what we did earlier, which is we start with our integral, and then we just simplify using the formula, and then solve it because it's a definite integral. Square root 9 minus x squared. So now just using those formulas from the previous page, what we're going to be doing is taking out a and propagating it through. So it just becomes, at this stage, sine minus 1 x, and then it's actually not just going to be x, it's going to be x over a, which in this case is 3, plus c, or rather, not plus c, because this is a definite integral, so we don't have to worry about that in this case. And instead, I'm defining the boundary conditions, and that's a 2, not a 3. And so from here, I'm just going to do exactly what I did on the previous question, and what you should always do when you have a definite integral, and just substitute in your upper boundary and then your lower boundary. And so from here, we're going to get this simplifying into sine inverse of 3 on 2, which is another way of writing 1 and 1/2, which will become a little bit clearer in a second. And then that's divided by 3. And then we're going, that should be minus sine inverse bracket 0 on 3. And again, no plus c. So then this becomes rather simple in that we get sine inverse, the 3 on 2 and the 3, so the 2 3's cancel, so we just get sine inverse of 1/2 minus sine minus 1 of 0. So again, the inverse sine of 0 is just going to be 0, so that's just going to disappear. But the inverse sine of 1/2, if you go back to your exact value triangles, is actually going to be 30 degrees, or rather it's going to be pi on 6 from if we're doing it in radians. So basically, if we're working with these sorts of weird fractions with the square roots on the bottom or multiple terms squared on the bottom, then what we're going to be doing here is they're going to become inverse trig terms, so inverse sine, inverse cos, and inverse tan. And it's really important to know which formulas are used where. So in this case, we had a square root on the bottom, which means it's sine or cos, and then we have to look at the plus or minus. And it's important to know how to change those formulas for when we have the a term, which is basically just, this is a squared, so we just square root whatever this term is, and then we just propagate it through using those formulas. It's important that you know those formulas and can work with them. Anyway, I hope that this lesson was helpful, and I will Hope to see you guys in the next one.